Hi everybody, I wanted to give everybody a quick rundown on building and deploying a pipeline for training the CheXNet model that came out of the paper out of Stanford for diagnosing one of 14 pathologies present in chest x-ray images. The dataset that was used to train this model is available at the box URL listed below from the NIH. Anybody can go and download it. The work that's been done here is a re-implementation of the model that was described in the paper, and I'm going to show you how to use some of the tooling that we've built in the Ready Solutions organization to build this pipeline locally on your laptop, and that should allow you to kind of poke and prod with all the tools and utilities that are available and that we've used to build this particular example. I'll start with a little overview. Again, we have this data set listed. We have a set of labeled x-ray images that we're using to diagnose one of the 14 pathologies present on the right-hand side of this slide. What the pipeline may look like, something along these lines. We have some historical data set that we use in our training pipeline to collect, and from this historical data we generate features. In our case, we won't be necessarily generating features. We do some light transformations on the images to downsample them, and our labels have already been provided for us in this particular example. We are going to be performing this experimentation loop that's listed here, where we train our model, we validate it, and we make tweaks to our model if we need to, and we continue through this iterative loop here. Once we have a model that we're satisfied with, we're going to publish that model out, and we already have a published model in this example, but I will show you how to publish a model out using this tooling. We will then load our model. In this case, loading it will be loading it into a TensorFlow serving instance, and then we can evaluate our model using live data. And the application logic that's listed here is just a Jupyter notebook that is an interface that allows us to upload images to a Kafka bus and then have our model evaluate it. The training pipeline will look something like this. We have this tool called Apache Airflow that allows us to define what are called directed acyclical graphs that can be used to describe workflows. In this example, we'll be using Airflow to describe the training workflow. Listed here, most of the boxes that are contained in this logical diagram are already defined in our tooling, and Airflow really just goes in and issues SSHs into a machine for us and issues the commands to make this particular process here, training our model, run. From a production pipeline perspective, we use some tooling that's available to build out the diagram that you see here, where we have an X-ray image that is input. In this case, this is an old slide, I apologize. This Flask server that's listed here is now actually a Jupyter notebook. These images are then published to a topic on Kafka, which then has a client that is listening on these particular topics to pick that image up as it's published and feed it into the TensorFlow model through the TensorFlow serving APIs, and then the results are published back to Kafka and picked back up on the Jupyter Notebook side of the house. Again, this is the kind of front end, or the data pipeline, if you will, and the rear of this would be the inference pipeline. Again, this should say Jupyter. However, an image is actually uploaded through Jupyter. We publish that image to Kafka. It gets published to this topic here, the inference image topic, and then the results are then collected and then displayed within Jupyter. I need to update this diagram. Thanks for bearing with me. And then the inference side of the pipeline is a client that has been implemented in Python that then again just makes API calls against the TensorFlow serving model to perform inference over an image, and I'll show you how that works. And the client logic looks something like this, where we have these, again, from a Kafka perspective, we have this inference image topic. We consume that image from Kafka. We do the image transforms that we need to do to downsample it to the 224 by 224 representation that we use for training the model. We perform inference over that model, again making an API call against the TensorFlow server. We then pass that message back onto the Kafka bus and consume it back into Jupyter for displaying what's going on, or displaying the results of our model. And with that, I'll show you what it would take for us to download the GitHub repository and get this running on our laptop today. So if you browse to this URL here, github.com/edhenry/chexnet, you'll be met with this page here. This is the entire repository and contains all the tools and utilities you should need to build this pipeline locally on whatever other device you want to build it on. It could be a server, it could be your laptop. So the first thing that we'll want to do, and before I get into that, I just want to show you what the Jupyter side of the world will look like. This is what we call a Jupyter notebook. You can see here that we outline what the use case is, so it's pathology detection in this particular case. There's a couple of example images that have already been run through our model, and this class activation map is this heat mapping that you're seeing here that allows us to understand what the, for lack of an anthropomorphic term, model was looking at as it was making the classification that it made. Again, we have a diagram here, and the updated diagram, Jupyter Notebook is listed. It covers some of the supporting services available, what some class activation maps are. It's got a little bit of code here that allows us to upload images and then publish them to Kafka. We then display the image. We wait for the results, so we collect the results back from Kafka, and we graph the probability of given pathologies, and then we have, again, class activation maps for these particular images. And I'm going to show you how to get this Jupyter Notebook running. So with that, the first thing that we'll want to do is we'll want to clone the repo. So we'll click clone or download and make sure that we're cloning the HTTPS version here. We can just copy this URL. We can pop a terminal. I'm just going to clone it to my downloads directory here. So I will go ahead and do that. And it may take a minute as there is a trained model and some data available within the repository. So some of the objects are kind of large that it's going to be pulling down. So I will pause the video and wait for it to finish. Okay, now that the repository is done downloading, we can change our directory into that downloaded directory. In this case, it's called CheXNet, same name as the repository. I'll make this window a little bigger here, potentially. Make this a little bigger and easier to read. So once we have our repository downloaded, we can take a look at the directory structure that's here, and you can see that there's a bunch of modules that relate to training and inference. This is the CheXNet client that was listed there. There's an example notebook, some data, all of the Docker files for this entire directory that are used to build out the client Docker image, the Jupyter Docker image, and the training Docker image. Generator py files used for generating data sets for training the model. But really what we're after here in this case is the playbook directory. So we can change directories into the playbook. And if we take a look at what's here, we see build site and destroy site and a host file. So I want to make sure that I've removed any trace of, and I haven't. So you get to see me actually destroy the site first before I build it. So we will go ahead and issue the command Ansible playbooks. The -I allows us to pass in a hosts file. And the host file just contains information about what host we want to execute the playbook on, and we'll destroy the site in this case. And if I issue that command, you can see here that the steps that are followed, it'll stop and destroy the entire site. In this case, it'll remove the CheXNet client service, the Airflow service, the TensorFlow serving service, Jupyter and Kafka, all of the services that are used to build and deploy this particular example. And now I'll go in and build it to rebuild the site. So we go ahead and issue build, and we sit back and we wait. We can see that Kafka gets built, a bunch of networking services. Just as a heads up, everyone, there are networking services that are built underneath the hood here as well, so you may have some trouble with VPNs, things like that, if you have anything defined on your host. And this should work on Windows as well, though I haven't had a chance to test it. And if anybody wants to test it and provide feedback, I'd love that. We can see here it's continuing to build all of the services. So we wait, and the last service to build is the Jupyter service. And if we take a look at all of the Docker images that are running, or Docker containers that are running on our host, we can see here that the latest version of our CheXNet Jupyter, so this is the Jupyter Notebook, is running, our client is running here, the TensorFlow serving instance is running, Airflow is running appropriately. It looks like Kafka came up. Everything looks stable and functional. From there, we can actually open a web browser, and we can browse to the Jupyter container that is running on our host. And I believe it should be 172.23.0.20, 8888. And we go ahead and enter the password, which is demo, to log into the box, and we're presented with this particular example. We can drill down into the Jupyter environment that's listed here, and we can see there's a directory that's listed within this Jupyter notebook, And we can see the CheXNet workflow example notebook that's here. If we click on that, it'll actually open that notebook that I showed you previously. And from here, we can actually interact with this environment. So all of these, this blue line here and the kind of box drawn around this particular, this is called a cell. This allows us to create logical segmentations of information within the Jupyter Notebook. So for this particular example, we've just created a description of what it is that we're trying to accomplish, description of the environment, all of the supporting services. And the real meat of this notebook and where it gets interesting is these code snippets that we have here. So if we go ahead and click the Run button on this particular example, all of the code that's in this particular cell has just been executed, and a good indicator of whether or not this cell has been executed is this little counter that gets incremented along with this little indicator here that shows that this cell has been run. And here we're going to define what is called a widget in a Jupyter Notebook context. You can also shift enter on a cell and it'll execute that cell for you, and you can see here that this little browse button was generated. So we're going to go ahead and click browse, and in this repository that we've downloaded, if I go to CheXNet and I go to example images, I can choose one of these example images to upload. So I click open, and you can see here that it uploaded that image, and then we can review the image. So again, we click on this particular cell and we shift enter, and it will actually display the images that we have uploaded. So here we create this bytes.io object that we pass that data from that upload widget into, and then we just open it and display it. Once we have that done, we can actually publish this image to Kafka. So this little publish producer.produce method allows us to do that. The return value of 0 is good. That means it was published. We can then retrieve the results. You can see here that if there is no response yet from the message or from the model, it'll say no new message. We do see here that we do have the response from our model, and this is the probability of all the different pathologies being present in this particular image. Looks like atelectasis is potentially what this particular model has classified this image as having, though effusion and infiltration are pretty high up there as well. And then we can display the class activation map for this image. Again, we have this display method that we can call, which is defined above, that allows us to display the image in the respectful class activation map. And you can see that the heat map is paying attention for some reason to the center of this particular chest, along with some of the artifacts around where there's maybe some gaps in the arm and the body of this particular patient. So again, the heat maps are providing, again, for lack of an anthropomorphic term, a bit of a understanding of what the model is looking at, if you will, as this diagnosis was produced. So this is an entire functional environment. I just wanted to give a quick overview of how to get this environment functional. And in other videos, I will explain the use case in further detail and start to decompose some of the components that are here to help you understand what all of these parts and pieces do.